Hello friends, I welcome you to my lecture on conversion of a boundary value problem into an integral equation. In my previous lecture, we discussed how we can convert an initial value problem into an integral equation, and the integral equation which resulted, it was a Volterra integral equation of the second kind. Then we also recovered back the initial value problem from the integral equation so obtained. Now what we are going to do here is that we will be taking a boundary value problem and we shall be converting it into an integral equation, and we shall see that we get a Fredholm integral equation of second kind, and then we shall recover back the initial the boundary value problem from the Fredholm integral equation so obtained. So let us see what do we mean by a boundary value problem first. When an ordinary differential equation is to be solved under conditions involving dependent variable or its derivatives at two different values of the independent variable, then the problem under consideration is called a boundary value problem. Let us consider the following boundary value problem. You see here we have a second order differential equation, d square by over dx square plus lambda y equal to x, where the values of the dependent variable by are given at two values of the independent variable, that is 0 and 1. We are given by 0 equal to 0, by 1 equal to 1. So we shall convert this boundary value problem into an integral equation, and we shall see that we get a Fredholm integral equation of second kind. So let us integrate both sides. We have d square by over dx square plus lambda into y equal to x, by 0 equal to 0 and by 1 equal to 1. Okay, now let us integrate both sides with respect to x from 0 to x. So then what do we have? Integral 0 to x d square by over dx square, lambda is a constant, so lambda into integral 0 to x by x dx, by is a function of x, equal to x square by 2 0 to x, and when you integrate here what you get is dy by dx, which is to be evaluated at the point 0 and x, and then we can write it as, now x square by 2 at x is x square by 2 and at 0 it is 0, so we get x square by 2 minus lambda integral 0 to x by x dx. Here what do we notice is that dy by dx at x is dy by dx minus dy by dx at 0. So dy by dx at 0 we can write as by prime 0, and this is x square by 2 minus lambda integral 0 to x by x dx. Now we are not given the value of y dash 0, so we can assume it to some constant. We can take it as c. So let us take y dash 0 equal to c. If we take y dash 0 equal to c, then we can write it as y dash x equal to x square by 2 minus lambda integral 0 to x by x dx plus c. Okay, again let us integrate with respect to x. So again when we integrate we shall have integral 0 to x by dash x dx equal to x square by 2 will become x cube by 6, and then we shall have minus lambda times 0 to x by x dx2, because we will have double integral here. Okay, when we integrate it again we shall have double integral plus c x 0 to x. Okay, now this will be by x minus by 0 on the left side, and here we shall have x cube by 6 And here we have double integral, so let us recall the formula which converts the n integrals into a single integral. So a to x by x dx, where this is n times, this is equal to 1 over n minus 1 factorial integral a to x minus t raised to the power n minus 1 into by t dt. So let us recall this formula. So here n is equal to 2, so we can write 1 over 2 minus 1 factorial, which is 1 factorial integral 0 to x and then x minus t into by t dt. And then here we have Cx. Okay, we are given by 0 equal to 0. So when you put by 0 equal to 0, what you get is by x equal to Cx plus x cube by 6 minus lambda 0 to x minus t by t dt. Now we have the values of by x here, and we also have the value of this thing by dash x, but c is unknown here. So what we will do is okay, so let us now put x equal to 1 to determine the value of c. So by 1, by 0 is 0, so by 1 equal to 1 by 6 minus lambda integral 0 to 1 minus t into by t dt plus c, and by 1 is equal to 1, so we get c equal to 5 by 6 plus lambda integral 0 to 1 minus t into by t dt. Now the value of c we substitute in this equation. Okay, so thus we have by x equal to x cube by 6 minus lambda 0 to x minus t into by t dt plus c into x. So c into x means pi by x by 6 plus lambda 0 to 1 x into 1 minus t into by t dt. Now we have to write it in terms of what we do is we break this interval 0 to 1 from 0 to x and then x to 1. So what we do, x cube by 6 minus lambda integral 0 to x minus t into by t dt plus 5x by 6, and then we write lambda times integral 0 to x times 1 minus t into by t dt plus x to 1 x times 1 minus t into by t dt. What we will do is we will combine the two integrals where the limits of integration are 0 to x. So we shall write it as by x equal to x cube by 6 plus 5x by 6, and then we shall write it as lambda times integral 0 to x times 1 minus t minus x minus t into by t dt plus integral x to 1 x times 1 minus t into by t dt. If you simplify this, what we get is x cube by 6 plus 5x by 6 plus lambda times integral 0 to x. Here we have x minus xt minus x plus t. So, we have t times 1 minus x into by t dt plus x to 1 x times 1 minus t into by t dt. Okay. Now, what we do is we can write this equation as or by x equal to x cube plus 5x by 6 plus integral 0 to 1 kxt, kxt is the kernel of the differential the integral equation into by t dt, where kxt is defined as t times 1 minus x, where t lies from 0 to x, and x times 1 minus t, where x is less than or equal to t less than or equal to 1. So, we see that the given boundary value problem is converted into this integral equation by x equal to x cube plus 5x by 6 plus lambda, here lambda is missing. So, lambda times integral 0 to 1 kxt by t dt, where kxt is t times 1 minus x, 0 less than or equal to t less than x, and x times 1 minus t when x is less than or equal to t less than or equal to 1. So, thus we obtain a Fredholm integral equation of the second kind. Now, let us see how we can recover the boundary value problem from this integral equation. Now, let us take one more example of a boundary value problem where we shall see how we can obtain the integral equation. We are given a differential equation of second order where the values of the dependent variable by are given at 2 points 0 and 1. So, again what we will do, we will integrate this differential equation with respect to x from 0 to x. When you differentiate, when you integrate d square by over dx square with respect to x, you get dy by dx, the limits of integration are 0 x, and then integral 0 to x 1 dx for this one on the right side, and then we have brought this term x by on the right side and we have written its integral. So, minus 0 to x, x into by x dx, by is a function of x. Now, when we integrate d square by over dx square and then put the limits of integration, what we will get, dy by dx, which we have written as by dash x, minus dy by dx at x equal to 0, which is by dash 0 as c we have defined. So, this c minus by dash 0 we have brought to the right side and written it as c, and here we get x. So, the limits of integration are 0 and x. So, we get x here minus 0 to x, x into by x dx. So, this is what we get. So, we have by dash x equal to x minus integral 0 to x, x into by x dx plus c, where by dash 0 is equal to c. Now, when we again integrate this, we get by x 0 to x, and here we get x square by 2 0 to x, and then we have double integral 0 to x So, this will become by x minus by 0 is equal to 0. So, by x equal to x square by 2 minus this double integral can be converted into a single integral minus 0 to x, x minus t into t by t dt plus c times x. So this is what we get. Now let us evaluate c by putting x equal to 1. So when you put x equal to 1 here, what you get is by 1 is equal to 0. So we get 0 equal to 1 by 2 minus integral 0 to 1 minus t into t by t dt plus c, or we can say c is equal to integral 0 to 1 minus t into t by t dt minus half. Okay, so c is, this gives c is equal to integral 0 to 1 minus t into t by t dt minus half. Okay, so let us substitute this value of c in this equation, and what we will have then? So substituting the value of c, we have yx equal to x square by 2 minus integral 0 to x, x minus t into t by t dt plus cx. So x times integral 0 to 1 minus t into t by t dt minus half x, or we can say this, we can write further as x into x minus 1 by 2 and minus integral 0 to x, x minus t into t by t dt, and this we can break into two parts again, 0 to x 1 minus t into t by t dt plus x to 1 minus t into t by t dt, and then we can combine the two integrals where the limits of integration are 0 to x and write it as x into x minus 1 by 2. So when we combine the two integrals where the limits of integration are 0 to x, we shall have integral 0 to x, x times 1 minus t into t minus x minus t into t by t dt, and then we shall have integral x to 1 x times 1 minus t into t by t dt. Okay, and then it can be further written as integral x times x minus 1 by 2 plus integral 0 to 1 kxt into by t dt, where kxt is equal to x into 1 minus t into t minus x minus t into t. So this is, if you simplify it, xt minus xt square we have, xt minus xt square, and here we will have minus xt plus xt square. When 0 is less than or equal to t less than x, and this will be x into t into 1 minus t when x is less than or equal to t less than or equal to 1. So this xt and this xt cancel, and what we get is xt times 1 minus t. So we have t square, xt square minus xt square. I think we have not written it correctly, just a moment. We have t square times 1 minus x. So here we have xt minus xt square minus xt plus t square we have. So this is this can be written as so t square times 1 minus x, 0 less than or equal to t less than x, and xt times 1 minus t 0 x less than or equal to t less than or equal to 1. So we see that we again get a Fredholm integral equation of the second kind by x equal to x into x minus 1 by 2 plus integral 0 to 1 kxt by t dt, where kxt is t square into 1 minus x, 0 less than or equal to t less than x, and xt times 1 minus t when x is less than or equal to t less than or equal to 1. So this is how we convert a boundary value problem into an integral equation, and we have seen that when we convert a boundary value problem into an integral equation, the resulting integral equation is a Fredholm integral equation of second kind. There is one more example, d square by over dx square plus by equal to x, where we have taken the two conditions on the dependent variable by. First condition is by at x equal to 0 is 0, and the second condition gives the derivative of by at x equal to 1, which is also given as equal to 0. So this is again a boundary value problem, and it can be similarly converted into an integral equation, which will be a Fredholm integral equation of the second kind. So let us convert this boundary value problem into an integral equation. So we have d square by over dx square plus by equal to x, where by 0 is 0 and by dash 1 is equal to 0. Okay, so we integrate it with respect to x from 0 to x. So dy by dx my plus integral 0 to x by x dx equal to x square by 2 integral 0 to x. So let us integrate the given differential equation with respect to x from 0 to x. So we will have by dash x minus by dash 0 plus integral 0 to x by x dx equal to x square by 2. By dash 0 let us assume to be equal to c. So then we will get r by dash x equal to integrals 0 to x by x dx. We will have to take it to the right side, so we put negative here, plus x square by 2 plus c, where c is equal to by dash 0. By dash 0 we have assumed equal to c. So by dash x equal to minus integral 0 to x by x dx plus x square by 2 plus c, and let us put x equal to 1 here. So putting x equal to 1, we have by dash 1 is equal to 0. So 0 equal to minus integral, we need not put, I think we need not put right now. Let us integrate it once again. Let us integrate it once again. So what we will get, by x equal to 0 to x minus double integral by x dx plus x cube by 6 plus cx. We have this, so this will give you by x minus by 0. By 0 is equal to 0, so we will get by x equal to by x equal to, now this double integral can be converted into a single integral, so minus integral 0 to x, x minus t into yt dt plus x cube by 6 plus cx. So we have got the value of by x, but we still do not know what is the value of c. So the value of c can be obtained from here. Let us say call it equation 1. So in equation 1 let us put x equal to 1. So in 1 put x equal to 1, then we get c as c equal to by dash 1 is 0, so we get integral 0 to 1 by x dx minus 1 by 2. So this value of c we substitute here and obtain the integral equation. So put the value of c here, so by x equal to minus integral 0 to x, x minus t into yt dt plus x cube by 6 plus we multiply that value of c by x, so integral 0 to 1 x into by x dx minus half x. Okay, now what we can combine this. So we can combine this as by x equal to x cube by 6 minus half x, and then this can be broken into two parts. Now here you can write t yt dt because it is a definite integral, so we can write integral 0 to 1 t yt dt and write it as minus integral 0 to x, x minus t into yt dt, and that can be broken into two parts, 0 to x t by t dt plus x to 1 t by t dt, and then this can be written as by x equal to x cube by 6 minus half x plus integral 0 to 1 kxt by t dt, where kxt is what we have t minus x minus t when 0 is less than or equal to t less than x, and we have t when x is less than or equal to t less than or equal to 1. This is nothing but 2t minus x, 0 less than or equal to t less than x, and t when x is less than or equal to t less than or equal to 1. So we can obtain the Fredholm integral equation of second kind by x equal to x cube by 6 minus half x plus integral 0 to 1 kxt by t dt, where kxt is given by this expression. So this is how we convert this boundary value problem into a Fredholm integral equation of second kind. This is what I have to say in this lecture. Thank you very much for your attention.